In the previous example, we designed a PI controller. At this point, I now want to discuss more generally the notion of PID control. Here's the transfer function of a PID controller. It has three terms where, in essence, the input is the error, the difference between the commanded reference and the actual output, and what the controller produces is a control input into the plant. And so if you bring the error over, you can see that the controller output is a constant times the error, which is the proportional part. This multiplication of s with the error, which gives you differentiation, so part of it is proportional to the derivative of the error, and then another part takes the error and divides it by s, which is equivalent to integration in the time domain, and multiplies it again by a constant. And so this part of the control is proportional to the integral of the error. This type of controller is very widely used in industry. I've heard people throw out numbers like 90% of all controllers used in industry are PID controllers. I don't know if that's quite correct, but they are very commonly used. And one reason that they're commonly used is they're very intuitive and easy to implement. Everybody understands what a derivative is, everybody understands what integration is, so they can understand the concept of the controller and they can implement it. Despite its simplicity, it's also relatively sophisticated in the sense that the control command isn't based only on the current error, which would be the part that's proportional to the current error, but it also depends on the history of the error, i.e. the integral of the error, and the anticipated future error, i.e. the derivative of the error. And so those notions might not make a ton of sense quite yet, but we will try and sort of delve into the PID controller a little bit more and build some intuition. The way that we're specifically going to build some intuition is we're going to look at the effect of the three terms of a PID controller, the P term, the D term, and the I term, in terms of its effect on a canonical second order plant. And so here is the transfer function for our plant or our process which we wish to control. If we found the closed loop transfer function, it has the form forward over 1 plus loop, again because it's a negative feedback system where the forward path from R to Y includes just C times P, and then you have 1 plus loop where the loop again only includes C times P. Rearranging, so substituting in for P of S and cleaning it up, this is the form of the closed loop transfer function, where C of S is the controller and A and B are properties of the plant. So here again is the closed loop transfer function. The first type of controller we'll look at is simply P control. So of the three terms, it only has the P term. A P controller, the control effort is proportional to the amount of error. So that's where the name comes from. And basically what it says is the output of the controller is just some constant multiplied by the error. And so the bigger the error, the bigger the application of control. The smaller the error, the smaller the application of control. If we substitute this into our closed loop transfer function, this is the result. So looking at this, this has a form very similar to a canonical second order system. It has no zeros, it has only two poles, and so if we match these coefficients in the denominator of the closed loop transfer function, we can match them to the parameters of a canonical second order system, which we understand. So specifically, this term maps to omega n squared. Taking the square root of both sides, we have that omega n is equal to the square root of b times 1 plus kp. And then looking at this coefficient, we have 2 zeta omega n is equal to a. If we solve for zeta, we can divide through by 2 and omega n, where we already have this expression for omega n. And we find that. So a few things to notice is that increasing Kp makes omega n larger. So you can sort of think of it as making the system stiffer. Increasing Kp also makes this quantity smaller, therefore it makes zeta smaller. So we can think of this as making the system stiffer. We can also think of increasing Kp as decreasing the damping. And these sorts of results are sort of intuitive. So by making the control effort proportional to the amount of error, if we increase Kp, it'll react harder to a specific amount of error. So for a given amount of error, we get a given amount of control. We increase Kp for that same amount of error, we're going to apply more control. So you can sort of imagine that the system would fight harder, push in one direction really hard. The error changes sign, it pushes really hard in the other direction, and it kind of rattles back and forth. So you can sort of imagine that it may overshoot more. You can imagine that maybe it'll oscillate with a higher frequency. Another thing that you'll notice is the fact that we have only one parameter Kp is we cannot set omega n and zeta independently. So if we choose Kp to give us some desired omega n, then we're going to end up with a specific zeta, which maybe is not the one that we want. So we only have one parameter, one knob to tune, so we can't set all of the parameters of a second order system independently. So that gives some intuition about the effect of P control on transient performance. Let's now look at the effect of P control on steady state performance. So again, we can find the steady state value by applying the final value theorem. So this is the final value theorem for an output y, the output of our closed loop system. Substituting in our transfer function. So this is our transfer function, and this is our input u of s, because we're doing a unit step reference. So this all together is y of s. The s from the input cancels the s from the final value theorem. Then this quantity has poles all in the left half plane because the coefficients of the denominator are all the same sign. This function is also defined at s equals 0, so we can solve the limit by simply subbing in for s equals 0. So we sub in 0 for s, that goes to 0, this goes to 0, and we're left with b times kp in the numerator and b times the quantity 1 plus kp in the denominator. That common factor of b cancels, and we end up with the final value of kp over 1 plus kp. So one thing that you'll notice is we've commanded a unit step reference. So we've essentially commanded the system with an input of 1. Yet the final value of our system does not go to 1. So you can sort of imagine a picture like this, where you've commanded 1, but the steady state output approaches some value different than 1. So with P control, we will have some amount of steady state error for a unit step reference. Go ahead and take a second and think about what could we do with Kp in order to reduce the steady state error. In order to reduce the steady state error, we in essence want to bring this quantity closer to 1. We want our output closer to the commanded input. And we can make this closer to 1 by increasing the value of Kp. As Kp gets large, this Kp will dominate the 1. So we'll have a large number plus 1 divided into a large number. And so the bigger Kp gets, the closer this is to 1. So that gives us some intuition about how we can reduce the steady state error. Of course, by increasing Kp to reduce the steady state error, we may get some other adverse effects, such as we may increase the overshoot or the oscillation in the performance of the system.